And first of all, thanks to the organizers for the kind invitation. Thanks to Joe and Gert, who made nice introductions to pyroclastic density currents that will be easier for me. As a conclusion of this series of talks, I would like to talk about natural data. I hope you will enjoy that. And today we'll present a very simple analysis of the factors that control the runout distance of pyroclastic density currents. Runout distance is a matter of concern for volcanologists in the context of hazard assessment. I did this work in collaboration with two volcanologists, Chris Henry and Alvaro Aravena, and four mathematicians at University of Clermont in France, Nourdine Azaoui, Arnaud Guillain, Laurent Chupin, and Thierry Dubois. This is a schematic representation of an explosive volcanic eruption during which a jet of gas and particles is injected in the atmosphere. The turbulent jet entrains the air. First, it rises up because of its momentum, then entrains and hits the air and becomes buoyant and forms what we call a volcanic plume. But in some cases, or during the course of an eruption, if not enough air is entrained, the mixture becomes more dense than the ambient atmosphere, falls back under the influence of gravity and forms what we call a pyroclastic fountain, which generates pyroclastic density currents, which are the subject of my talk today. Volcanologists have known for decades that the plume height increases with the mass eruption rate. This is a compilation made by Mastin and collaborators, which gathers data of more than 30 well-documented eruptions, and which shows that the mass eruption rate increases that the plume height increases with the mass eruption rate according to this power law. So since the plume height depends on the flow rate, and since plumes may collapse to form pyroclastic density currents, today I will address the following question. Does the runout of pyroclastic density currents depend also on the mass discharge rate? So for this, we did a quantitative analysis of natural data, and we created a database gathering data of nearly 50 pyroclastic density currents described in more than 80 publications. The volume of the eruptions that generated these currents vary over 7 orders of magnitude and can be as high as 1,000 cubic kilometers. And the runout distance of the currents varies from about 3 kilometers to more than 100 kilometers. And the mass eruption rate varies over 5 orders of magnitude. So we consider two end-member mechanisms of emplacement of pyroclastic density currents. Joe and Gert have mentioned this before. On one hand, we consider dilute currents, which are dilute turbulent flows with particle concentrations typically less than 1 volume%. Of course, as just mentioned by Gert, there can be important particle concentration gradients, formation of clusters, etc. And as the turbulent flow is hot and entrains the ambient air, at some point the mixture can become less dense than the atmosphere and lifts off, and this sets the runout distance. On the other hand, one may consider a concentrated basal granular flow represented here, whose dynamics is dominated by particle interactions and possibly gas pore pressure, and this dense flow is overridden by a turbulent flow. This forms a two-layer current. So in this talk, when I say concentrated flow, I mean the concentrated basal part of a two-layer flow. So in both cases, the current loses mass through particle settling, which occurs at a typical velocity W, either from the turbulent suspension or from the concentrated current. And the consequence of particle settling is to form a deposit, of course, as just illustrated by the videos shown by Gert. So now let's consider the two parameters of interest for our study. First, the runout distance. So there are many uncertainties in estimating the runout distance. So we considered the maps given in publication, and in most cases, the currents spread radially from the eruptive center and form subcircular deposits. So we took the map in the publications and measured the runout distance in subperpendicular directions, calculated a mean value, and consider the minimum and the maximum estimates. As you can see on this picture, when the erosion is old, of course, the deposit is partially eroded. Considering the eruption rates, it is most often given in the literature for the initial plume phase, number 1, and it is calculated from the plume height. So in that case, we had to make a correction to obtain the eruption rate for the flow phase, and I will explain this correction in the next slide. In fewer cases, we've got estimates of the eruption rate for the flow phase, either from models of emplacement of pyroclastic density currents, or considering mean values from the ratio of the volume of the deposit divided by the duration of the eruption. So now I'm going to explain how we made the correction. In fact, there are very few cases for which the eruption rate is known for both the initial plume phase and for the subsequent flow phase. In fact, we found 9 well-documented eruptions described in the literature. Their names are given here. This graph shows the mass eruption rate, and the values are ranked by increasing values for the plume phase, and corresponding values are shown also for the flow phase. Considering the plane and dashed line, we show that on average, the rate during the flow phase is 1 order of magnitude, exactly 14 times higher than during the plume phase. So as we've got most often from the literature, the flow rate from the plume phase, we multiplied the values we've got by a factor of 14 to get the eruption rate for the flow phase, which is what we are interested in our case. No, it's just to get increasing values. Okay, from the smallest to the highest value. And here are the results. So this is the runout of the current as a function of the mass eruption rate. The data are presented for both the dilute and concentrated flows. We've got respectively 14 and 28 data points. And the data show 2 well-defined power law relationships with coefficients of determination of 0.91 and 0.95. And from now, I'm going to discuss the values of the exponents, which are respectively 0.47 and 0.37. So first, let's consider the dilute currents. We've got 14 data points in that case. And as a comparison, I show here the runout distance of flows that traveled over water. In all of our cases, the flows traveled on land. Now let's consider a bit of a theory. In an earlier publication on the runout distance of turbidity currents, Dade and Duppert have shown that the runout distance of these currents and of turbulent fluid particle flows in general scale with the ratio of the volume flow rate divided by the particle setting to the power 1/2. In fact, this term has the dimension of length and shows that the runout depends basically on the balance between particle advection and mass loss through particle settling. Okay? In our case, we consider the mass flow rate, but we assume a constant solid density to convert the flow rate to the volume flow rate to the mass flow rate. So in principle, the runout should scale equally with the ratio of the mass flow rate divided by the settling velocity to the power 1/2. So what we did here, we estimated settling velocities for each cases here, considering typical grain sizes. This is obviously another simplification, especially if we consider that clusters can form and can enhance the settling velocity, of course. But then, with these estimated velocities, we can calculate the ratio Q over W, and we obtain this new power law relationship, which shows that in that case, the exponent is closer to the theoretical value of 0.5, and also the power law is better defined since the coefficient of determination is 0.95. And finally, you can see that there is a tendency for the flows that travel over water, but there are only 5 data points. And this suggests that at a given ratio Q over W, these flows over water traveled twice as far as they do on land. Yeah.
I have just a small question. You have this exponent experimentally, but I guess you can have the error bar on the exponent considering the error bar on your data point.
Are you considering here?
No, yeah, you have an exponent.
Yeah.
Okay, and you have data with error bars, and
Yeah.
you can estimate the error on the determination of the.
So we have
yeah.
we have calculated prediction and confidence intervals, and I can show you. Is that what you mean?
Maybe, I don't know.
Maybe later.
I will have a final
I think
slide
the question is
if you are
simply, what's the
interested.
uncertainty on 0.47?
Yeah.
Is it the same as 0.5?
Just a word on the corrections we made. If we consider non-corrected mass flow rate, we obtain this exponent, which is significantly smaller than 0.5. And this suggests that the corrections we made are relevant and necessary. Okay, now so let's talk about the data of the concentrated current. These are the data I've shown before. And here I show in addition the 90, 95, and 99% prediction intervals calculated from these data. So as I said earlier, in most cases, the flow spread radially and forms subcircular deposits, but this is not always the case. As illustrated by this figure showing the approximate contours of deposits formed by concentrated pyroclastic density currents, the eruption occurred in a Great Basin area in the western US quite a long time ago. The eruptions are 20 to 30 million years old. And the volumes of the eruption vary from 300 to 1,800 cubic kilometers. You may note the scale on these simplified maps. And as you can see, the deposits are not subcircular, they are rather elliptical and clearly elongated in the east-west direction, because in fact, the flows were channelized by large paleovalleys, which enhance the runout distance. So we did simple calculations here. First, we calculated the runout distance in the north-south direction. The data are presented by the yellow dots here, and they fall within the prediction intervals for the concentrated currents, almost all. Instead, if we consider the runout distance to the east, as shown by the triangles here, the data are clearly outside these prediction intervals, and they are even outside the prediction interval for the dilute currents. And the longer runout distance is more than 300 kilometers. So channelization clearly contributed to enhance runout distance, but the slope angle of the topography could have also contributed. And we can get insights on this mechanism from simulation of dam break gas particle flow at the laboratory scale. So this figure shows the emplacement of a dam break gas particle flow consisting on the release of a fluidized granular column. And the simulation is based on a model of a two-phase flow, non-depth average model written by my colleagues. And the aim is to simulate this experimental configuration. I did this experiment quite a long time ago. This is a granular column of particles of 80 microns, which is fluidized by injecting air through a basal porous plate. And this generates gas pore pressure in the column. Then the granular column is released. Yes. And as pore pressure is maintained for a long duration during propagation of the flow, the runout distance is relatively long and the deposit is nearly flat. And this is in contrast with the release of a dry granular column. In that case, the runout is much smaller and the deposit is more steeply inclined. Okay, so to take into account this experimental configuration in the model, the pressure, solid pressure is counterbalanced by the gas pore pressure. And we assume that it diffuses according to, it decreases with time according to a diffusion coefficient. So Alvaro Aravena did simulations at different slope angles, and this graph shows that the runout distance normalized by the runout distance on your horizontal substrate increases significantly with the slope angle. For example, at 5 degrees, the increase is by 40%. So we have seen that in case of large volume eruptions, the flow was channelized. But in fact, considering the data in our database, this is also the case for some of the cases here represented by the red dots with the black contours. In that case, because of topographic effects of because of eruptive conditions, the flows were directed into a main preferential direction, or they were channelized by valleys oriented radially from the vent. So here we corrected the runout distance using a simple method. We calculated the area of the deposits and then considered the radius of circles of equivalent areas. And with these corrections, we obtained this trend, which is superparallel to that for the dilute currents and with an exponent of 0.51. So what about, so I remind you that we are interested in also the ratio of the flow rate divided by the settling velocity. So what about the settling velocity in concentrated currents? The problem is that we have no mean to calculate this velocity because this issue is poorly known. But in principle, these currents obey to the same principle as the dilute currents. The particles settle at a typical velocity W. This creates deposits and the so-called static mobile interface, which migrates upwards as the deposits form, and this occurs at a typical velocity U. This is illustrated on this video. The flow head slides, onset of deposition occurs, and then the static mobile interface migrates upward at a fairly constant velocity that we can measure in experiments. So, to estimate the particle settling velocity in the concentrated currents, we use the following method. I remind you that for dilute and concentrated currents, all parameters, runout distance, flow rate, and settling velocities are known, except the settling velocity for the dilute currents. So here we made the following hypothesis. As for dilute currents, the runout of concentrated currents depends on the ratio of the flow rate divided by the settling velocity. And the aim is to find the unknowns alpha and mu, given here, and also WC, the settling velocity, that minimize the following cost function. So the resolution was made by my colleagues through an iterative procedure, and they have found that, on average, the settling velocity is equal to 4.8 plus or minus 2 meters per second. So what does this mean? These values are one order of magnitude larger than what we observe in experiments, which may have different meanings. Either this model is wrong, or there is a scaling issue between nature and experiments, or both, maybe. And with these values of settling velocity, we can calculate the ratio Q over W and obtain the following trend, which is nearly coincident to that for the dilute currents. And considering the whole set of data and the theoretical exponent of 0.5, we can define a kind of master curve for the flows irrespective of their physics. So in summary, our study suggests that the eruption rate is the main control parameter on the runout distance of pyroclastic density currents. In detail, this runout distance scales with the ratio of the flow rate divided by the settling velocity to the power 1/2 in agreement with theory. And as we can see, at least for dilute currents, we can show that the settling velocity has a second order influence. And finally, we have estimated settling velocity in concentrated currents, but this issue clearly needs further investigation. So as a final conclusion, I will say that pyroclastic density currents are very complex multiphase flows, but our study suggests that their runout distance can be described at least at first order in very simple terms, and this is the message I wanted to deliver today. Thank you.
Questions for Olivier? Let's do Doug and then Michel.
Hey, thanks for a great talk. This is inspired by your talk, but maybe a broader question. So there's been a lot of talk here about enhanced settling in these turbulent flows. And the funny thing coming from the suspension world is I'm used to hindered settling when concentrations get high enough where actually, right, the sedimentation rate slows down by a lot. But of course, hindered settling is most often studied in static or more quiescent flows. So yeah. I don't know what to ask except somehow what's the addressing between enhanced settling and hindered settling in concentrated flows? Is there like a switch that gets flipped at some amount of turbulent shear? I don't know.
I'm concentrated, no, I would say, I would ask the question rather for dilute flows. Because, for example, as Gert shows, the clusters form in what we consider as dilute flows. And I don't know what to answer, but maybe I invite you to have a discussion with Michael and I, because we have done experiments recently on turbulent suspension where clusters form, and we show that in some cases there is inert settling, and in other cases there's enhanced settling. So I'm sorry for this answer. This is not based on the presentation, but I think that's the best answer I can give you.
But you might share some of these results in the next.
Possibly, if you are interested in, okay. But okay, I see what you mean.
Yeah, Olivier, so imagine you go to the store and you buy a brick of those vacuum-packed coffee, and it's hard, and you put a little hole in the top, and then you could see a diffusion of the front that will eventually engulf.
You put what?
You have these coffee, these bricks of coffee that you buy at the store.
Yeah.
And they're packed under some vacuum.
Yeah, I see.
Right. So you pierce a hole at the top, and then there's a diffusion that takes place that can be relatively easily predicted with Darcy's law and the mass conservation equation. So that leads to a diffusion coefficient. So what my question is why couldn't this concentrated current velocity that you measured, couldn't it be predicted that way using the permeability of the
settling velocity?
Yeah. So in principle, there's a direct diffusion coefficient you could get from K, rho, and stuff like that.
I mean, my probably naive view is that this settling velocity is controlled by what happens at the static mobile interface. And my naive view is that there should be a kind of equilibrium between a driving stress and a resisting stress. And I see a kind of similarity with the Shields number you consider, when particles are entrained or deposited. So I would rather think in terms of balance between shear stress generated by the flowing media and resisting stress, maybe related to the weight of the particle or something like that. What I can tell you is that in experiments, when we measure the degradation velocity, it's different for initially dry flows and initially fluidized flows. So pore pressure acts. And, but honestly, I don't know any, or maybe I've missed something, I'm not a physicist. I don't know any papers predicting the settling. Deposition velocity and settling velocity in granular flows. This is observed in simulations, for example. And this is something we have done. I mentioned the model written by my colleagues. It's non-depth average. So in the model, we can trace the static mobile interface. So now what we are trying to do is to determine the condition at this static mobile interface. This could be possible from the numerical results.
Olivier, in some of your plots, you had some points for flows that traveled over water.
Yeah.
And you mentioned, and you showed that they traveled quite a bit further than ones over land.
Yeah. Oops.
Do you have an explanation for why?
I think Joe maybe has an explanation because he worked on that.
But the explanation was that they created a raft of floating particles, and so they look like they traveled over land.
Joe, please.
In our calculations, they went further because you lose energy to saltation over land. So we had a kind of a leaky energy condition when you're saltating on land. So that's how we got it. But yours is very different, though, right? It could be other reasons too.
Yeah. And it's something we discussed also with Gert last week. Maybe also with the hot flow. Maybe yes, is able to boil some water, which creates a source of fluidizing gas, which may retard the particle settling, maybe. But there are only 5 data points here. But don't forget that these are log scales, so the difference is not negligible.
This is kind of a follow-up to, oh my gosh, names slip my mind. Anyway, on the accelerated settling, I'm sorry, Doug, it's like, this is what happens to me when I'm at the end of the conference. Anyway, sorry. Is there I mean, we have a hand-waving theory or hand-waving explanation for hindered settling. Is there a hand-waving explanation for accelerated settling?
Here? You mean, sorry.
Do you have a quick explanation for what causes accelerated settling?
Enhanced settling?
Yes,
Well,
enhanced settling.
In dilute flows, it can be the formation of clusters. The clusters settle at a velocity that is larger than that of the individual particles. Well,
So is it that the particles, like when you say they form clusters, is it actually, what I'm picturing is it could either be like a rigid, at least a quasi-rigid structure until it falls apart, or it's a bunch of particles that are all kind of, I don't know, pulled together by turbulence and then therefore kind of drafting off of each other?
maybe Gerd can answer because, do you want to answer, Gerd? Or? No, I mean, what,
No, you don't want me to.
if I understand, what we mean by particle settling are zones of higher particle concentration. These are not aggregates.
Okay,
Okay?
that's the cluster.
Do you agree? Okay.
Your second idea.
Okay, thank you.
And sorry.
So where you have a particle cluster, where you have a particle cluster, the particles drag down the air or the water with them. And so as a result, the particles effectively settle in downward moving fluid. And so that's why they settle faster. That's one way to look at it.
Well, the other way is also that the size is bigger. Even in Stokes flow, the size of a cluster will be bigger than the size of an individual particles. And since the Stokes velocity is going like the square of the diameter, it's settling.
It's not a rigid particle, right?
Yeah, but
No.
And it seems like, isn't that the opposite of, I mean, it's essentially effectively the explanation for hindered settling, right? But it's inverse of that, because the hindered settling, something's in the way of the part of the fluid moving out of the way. And in the other way, the fluid is moving with it, and so it's sort of pulling it. I don't know. It seems like interesting thing for
Kimberly, the intersettling, if you think about for instance, the Richardson-Zaki law, which is showing the intersettling for homogeneous suspension, is really due to the fact that if you compute things just by looking in interaction with particle, you will find that it's going faster, but there is a bottom of the container which is inducing a backflow. That's why you have intersettling, and it's stronger.
Right, so it seems like the opposite thing that's happening for accelerated settling, right? Because in one case, there's fluid coming back caused by particle settling. In the other case, the fluid is going down caused by the particle settling. So it does seem like it's...
And that can come back up away from the cluster.
Yeah.
And so the question is really, where is the upflow happening? Does it need to go through the cluster or around the cluster? So on that note, I want to thank Olivier again. I also want to thank all of those who came here to present and share their science. And unfortunately, not everyone had the opportunity to share their science, either with a talk or a poster, but you engaged in a very lively discussion. And so I'd like to thank everyone who's still here and those who joined us online.
And don't forget, we have the barbecue at 6 o'clock. Barbecue at 6 o'clock at the Munger residence. Potluck barbecue.